Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now. To be or not to be sounds familiar, na?
Yeah, all the literature and philosophy lovers out there definitely know that phrase.
Of course we do.
Anyways, let's forget all the Shakespearean nonsense for now, and let's talk about the real stuff.
Okay, you're in luck today because we're going to talk about how to be and not to be.
Oho, bata bhai.
Okay, let's say you're playing basketball and you just shot a three-pointer and it's still in the air. Do you think you can predict the motion of the ball after it leaves your hand?
Sure, that's easy. The ball will move upward until it gets to some highest point called the vertex, and then it'll come back down and land in the hoop. Or you'll just miss and it won't.
Which is the case with you.
Please, okay?
Of course, that's what happens, and you know this because you have witnessed events like this countless times. We can literally plot the trajectory of a cricket ball, and that's how third umpire systems work.
Exactly. Similarly, Marcus Brownlee from MKBHD recently showed us how this trajectory planning and creation happens in golf in real time.
Yeah, what an interesting video.
True.
But back to the point. So you've been observing the physics of everyday phenomena your entire life. And since we already did an episode on quarks, you may know that the physics that governs the behavior of systems at such small scales is much different than the physics of the macroscopic objects that you see around all the time, basically.
Yeah, and when we say different, we mean like really different.
Yeah.
An illustration of this so-called quantum strangeness is given by a famous thought experiment. Schrödinger's cat. A physicist who doesn't necessarily like cats puts a cat in a box along with a bomb that has a 50% chance of blowing up after the lid is closed. Until we open the box, there's no way of knowing whether the bomb exploded or not.
Yeah.
And thus, we don't know if the cat is alive or dead. In quantum physics, we could thus say that before our observation, the cat was in a superposition state. It was neither alive nor dead, but rather in a mixture of both possibilities, with a 50% chance for each.
So philosophical. Literally Socrates and Plato type of stuff.
True, fine, fair enough.
This may seem absurd, which was basically Schrödinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory that he helped make and basically turned to writing biology.
Amateur, for real.
Of course.
So, what we're saying is, the cat is both alive and dead at the same time. The same sort of thing happens to physical systems at quantum scales, like an electron orbiting in a hydrogen atom. The electron isn't really orbiting at all, it's sort of everywhere, all at once, with more of a probability of being at some places than others. And it's only after we measure its position that we can pinpoint where it is at that moment, like Heisenberg's uncertainty principle.
Yeah. And this is a lot like how we didn't know whether the cat was alive or dead until we opened the box, right?
True.
This brings us to the strange and beautiful phenomenon of quantum entanglement.
Big words.
Yeah. Which we will explore in depth in another episode. Like, how do we create quantum entangled particles in the first place?
True.
But suppose that the cat, instead of one cat in a box, we have two cats in two different boxes. If we repeat this Schrödinger's cat experiment with this pair of cats, the outcome of the experiment can be one of four possibilities. Either both cats will be alive or both will be dead, or one will be alive and the other dead, or vice versa. Kind of like the heads tails things that we did in our entropy episode, basically.
So the system of both cats is again in a superposition state, with each outcome having a 25% chance rather than a 50% chance. But abhi to party shuru hui hai.
Uh-huh.
Quantum mechanics tells us that it's possible to erase the both alive and both dead outcomes from the state. Basically, there can be a two-cat system such that the outcome will always be one's alive and one's dead.
So predictable.
Literally.
Highly unlikely from quantum physics.
The technical term for this is that the states of the cats are entangled. But there's something truly mind-boggling about quantum entanglement.
If you prepare the system of two cats in boxes in this entangled state, then move the boxes to opposite ends of the universe and the outcome of the experiment will still remain the same. One cat will always come out alive and the other cat will always end up dead, even though with which particular cat lives or dies is completely undermined before we measure the outcome. But how is this possible, you may ask?
Yeah, how is it like that the states of the cats on literally opposite sides of the universe can be entangled in this way? They're like too far away to communicate with each other, and if they are communicating with each other by sending a signal, that literally has to travel way faster than the speed of light. So how do the two bombs always conspire that such that one blows up and the other doesn't?
You might be thinking, what is this time pass? This thing can't even happen in the real world, so why do I even care about it? But it turns out that quantum entanglement has been confirmed in real world lab experiments. Two subatomic particles entangled in a superposition state. Here, if one spins one way, then the other must spin the other way. Even when there's no way for information to pass from one particle to the other, indicating which way to spin to obey the rules of quantum entanglement.
And that's why it's not surprising that entanglement is at the core of quantum information science, a growing field study on how to use the laws of the strange quantum world in a macroscopic world, like in cryptography. So spies can send secure messages to each other, or quantum computing for cracking secret codes.
Yeah. As absurd as it may seem, Schrödinger's cat is very real. In fact, it's essential. If it weren't for quantum objects to be in two states at once, the phone that you're listening this episode on basically wouldn't exist, right? The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything.
Oh, wait, what? Wave particle duality?
Yeah.
Okay, so in order for an object to have a wavelength, it must extend over some region of space, which means that it occupies many positions at the same time.
Correct.
The wavelength of an object, limited to that small region of space, can't be perfectly defined though, so it exists in many different wavelengths at the same time.
Yeah. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases. And the cat is relatively bada and mota.
Compared to what, bhai?
Wait for it. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would seem just as small as an atom within that solar system. That's too far to detect, so we'll never see wave behavior from a cat.
I mean, expected, right?
Of course. A tiny particle like an electron can show dramatic evidence of this dual nature though.
Yeah, let's say the famous Young's double slit experiment, for example. If we shoot electrons one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, and you'll have to keep track of all the individual detections, you'll eventually see them trace out a pattern that's characteristic of wave behavior. A set of stripes. Regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time.
A single electron isn't choosing to go left or right, but left and right simultaneously.
Ooh.
This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread out wave-like orbit, which we now call an orbital. Bring two atoms together, and the electrons don't need to choose just one atom, but they are essentially shared between them. This is how chemical bonds form.
An electron in a molecule isn't on just atom A or atom B, but both A and B. So if you add more atoms, the electrons spread out more, and they're shared between vast number of atoms at the same time. The electrons, for example, in a solid or in a metal, they aren't bound to a particular atom, but they're shared among all of them, extending over a large range of space, and that's how you get free electrons and conductivity and electricity.
Damn. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor or an insulator or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials, like silicon.
I mean, that's really, really important for our daily lives.
Yeah.
So, let's combine different semiconductors, and if we do that in the right way, it allows us to make transistors on a tiny scale. Millions on a single computer chip. Those chips and their spread out electrons power the computer you're using right now.
You know, they say that the internet was basically made for sharing cat videos.
Really?
Yeah, but the philosopher in me would say that the internet owes its existence to an Austrian physicist and his imaginary cat.
Laser beam? Oh no, wait, sorry, he's Australian.
Schrödinger, come on.